Hello. We want to discuss energy conservation in a fluid flow. And when we derive an equation based on energy conservation, um, in the case of in the case when fluid does not have much viscosity, then that equation is called Bernoulli's equation. So always we focus in a fluid flow. Normally we focus at 2 points in the fluid flow, and in the space or the fluid between the 2 points, their properties are we kind of make use of it. So when we derive the equation of continuity, like A1, B1 equals to V2, we said, well, in between space, all the fluid was incompressible. The volume did not change much. Okay. Here we're gonna do a very similar approach. We will say that let's look at point 1. That's called 1. There's fluid before that also. May or may not be, but they will be coming in if there's a fluid flow, fluid before that. If not, then there's some kind of plunger or something pushing on the fluid. Nonetheless, there is a point 1 and then there is a point 2 in the fluid. Okay, and all the other properties will level with 1 or 2. So you will see that if something, maybe a plunger or a pump is having a pushing on the fluid, so we'll say this is some agent outside of my system. So this is my system. So we want to study how this system's energy can be affected. So whatever energy it has some energy. All right. So that we can just say it has a zero energy at this point. That's a reference energy. Well, you can see that this P1 is some agent outside the system. It's going to push and do some kind of positive work in the system. It's going to give some energy in the system. On the other end, when the fluid is coming out, it's pushing against something else. If this pipe is open, so it's pushing against atmospheric pressure. First, atmosphere is pushing it back, keeping it from flowing, but the fluid wants to go out. So if the fluid is successful in flowing, that means it has the atmosphere will have done negative work, taken energy out of the fluid. Okay, so the energy comes out here when the whatever pressure. There may be other pressures. There may be fluid. It doesn't have to be atmosphere. It may be the rest of the fluid. So rest of the fluid is pushing back. So rest of the fluid is going to be taking energy out from the system between 1 and 2. So P1 and P2, you can make sure that this is pressure is that way. You're pressing against outside. Okay. So how much work? Let's look at during delta T. Let's look at the energy that's coming into the system. So energy in. Let's write this down as a positive number. P1 times how much is able to push. Well, if this was the surface of the fluid and you had a plunger would have gone up to that far, right? And there's a V1 times delta T. That's how far it will gone. So it will be P1 times the area. That's the force. So the work is force parallel times D, right? So force is parallel, and the distance traveled is V1 times delta T. What's not clear, right? if there's a fluid here before, no plunger, there's a fluid flowing, right? So there's fluid, this will bring kinetic energy. This will bring kinetic energy in there. So how much kinetic energy is going to bring? That should be half mv square, v1 square. What's the m? Well, how much fluid is going to come inside? Well, it's going to come inside. It will have a density times the volume that will come inside in times delta T. So that's how much fluid is coming inside, right? So we will have half rho times A times V1, A times V1 times delta T, right? So that amount of fluid that's in here is that in this volume, so rho times A1 times V1 times delta T, this mass of fluid coming in times V1 square. Okay, so how much is the potential energy? The fluid that's coming in brought some potential energy. So rho times A1 V1 delta T times GH1. So this much energy is coming inside this space at this point. How much energy is leaving over there? Well, we can account for that by writing it will be negative value, right? So I'm going to write as a positive, just absolute. So P2 times that will, in terms of magnitude, P2A, that's the force, and times V2 times delta T. That's how much work must be done against the outside pressure. And then it would be similar kind of thing. That much mass will have to come out. So rho A2 V2 delta T times V2 square, half mv square, plus rho times A2 V2 times delta T times GH2. That's how much energy left, and that's how much energy came in. But the energy of the system would not change because there are no viscous forces. So this has to equal to that. And not only that, that has to be equal to that, but also there is a flow rate relationship. That also has to be true. So what we get an equation E in equals to E out. And the second one I get is A1 V1 must be A2 V2 from the continuity. Well, this E in equals E out, it's pretty complicated expression, right? This is A1, and this should be A2. It's a complicated expression, but when you do A1 V1 to A2 V2, you can say that I can just call this guy A1 V1, call this one A1 V1, call this A1 V1. So when make this equal to that, you can see right away that when I make this equal to that, this A1 V1 will cancel from A1 V1. This A1, all of them is A1 V1. And so all these A1 V1s will cancel out. So you can see that delta T also cancels out. Delta T is common. Oh, this delta T is common to all of them. And they should rightly cancel because delta T was arbitrary. So what it tells me is E in equals to E out. Using that, really simplifies. It says P1 pressure over here plus half rho V1 square, like a density kinetic energy density, half rho V1 square. And this looks like a potential energy density, not M, but density, plus rho GH1 will be equal to the corresponding property over here. So what's the, except that the P is pressing in and this P2 is pressing from the other end, you know, plus half rho V2 square plus rho GH2. So it is a different relationship for the pressure. So if the V's were 0, right, then the difference in the pressure will be difference rho GH, difference in heights. You can see there, right? But when the V is not 0, the pressure is like this. This is more complete picture than what we have done in the static. And this is called Bernoulli equation. This is an important equation. You may want to remember it. The way to remember it is not as an equation like this, but it's a thing which is this compressor plus half kinetic energy densities. So this is instead of mv square, use a density. Then it's a potential energy density. This is same. So I remember that this is same. So I can set it up as a I take two places in the fluid, and then I can set it up as an equation, right? There are many applications of it. In the next video or some video associated with this, I'm going to attach more videos to this. We'll talk about some of the applications of Bernoulli, and there are many. And really, I wish I had a demo room access, could show you some of the cool demos that go with Bernoulli. Maybe I'll look it up on online. There must be many demos of Bernoulli. All right.